Yes, maybe we can start.
Okay. Yeah, sorry, I said it in Spanish. I forgot to say it in English, but I think yeah, they're already translated, right?
Yeah.
Okay.
Yes, translated. Okay. Okay. Welcome everyone. Our speaker is Dr. Tonatiuh Hernandez del Toro. He is a scientist. He is a researcher in the field of data science, artificial intelligence, and quantum computing. He get his PhD from the Tonatiuh Research Institute in Hawaii. In which year?
In 2022.
In 2022. And he is actually a student from here. He did his licenciatura and maestria here with quantum computing. Presently, he is working in QHDL as an adjunctive professor, and he is also the lead of data science research in IBM. So today, his talk is methods to identify imaged words in continuous EEG signals.
Yeah, thank you. I'll tell you about some parts of the work that I did during the PhD. Back in that time, there were no LLMs, so we used to work with crude AI models. And the applications that we did, I was adjoined to the department or the laboratory of biosignals. So we applied biosignals to detect many stuff we would want. So basically, methods to identify imagined words in continuous EEG signals. Well, first, what is imagined words? What is a continuous EEG signal? Well, maybe that's most common, but first question, why do we want to detect this? Well, so before we describe what are exactly those things, first, I would like to introduce a new concept that may be not so popular, that is a brain-computer interface, or a BCI. That basically, the abstract concept is very simple. It's just a system that takes any type of brain waves. It could be, in our case, EEG, that is electroencephalogram waves that detect electric activity through our scalp. But it can be also MRI, functional near-infrared system, and any other brainwave detection you want. And with these brainwaves, you should be able, or the concept is that you can control an external system. You can control an external system, and this external system can be to move whatever you want or to interact with any other device you want. So in order to move this type of machines, they currently exist. They are kind of primitive still, but they work for many people that are impaired persons or people that have lost an arm or a leg. So they kind of have this robotic leg that can be controlled by their mind. It's very expensive. And in most of cases, they need to have a surgery, so it's invasive. They have to open your scalp and then put some type of electrodes or any other receptor of the signal. So we have many neuroparadigms. That's what we call the way of controlling this BCI. The first one was something called movement imagery. That is just like it sounds. You imagine to move your arm. But for people that do not have an arm, they can still imagine it. And it turns out that our brain do the same action over and over again. So when we imagine how to move my arm, and I do it again and again, my signal is going to be the same. So we should be able to detect those patterns to control. We have movement imagery. We have another that is visual evoked potential. That is basically you are in front of a screen and you have a grid with all the alphabet from A to Z, and each of the letters blink at a different frequency. Let's say 20 hertz or something. And for some reason, that is very interesting. That was not the focus of my research, but for some reason, our brain syncs with the frequency. So if we are blinking at 20 hertz, system, our brain detects those 20 hertz, so you can do a Fourier transform and you detect that spike. It's very interesting, but it's very slow. So that's when we come with imaging speech. Imaging speech is the action of speak internally without producing any sound or without moving any muscle. It's not silent speech. It's not that whispering. It's like directly in your mind, like when we are reading to ourselves without moving anything. That is the concept of imagined speech. We select this one because it's like the most natural way of communication to all humans. And it provides us with a wide dictionary of words to control whatever we want, in contrast to the movement, the imagined movement. So far, we can now understand the title, identify imagined words. So identify the action of me imagining word in EEG signals. Why? Because we want to control an external system with my words. In this case, it could be a pointer, up, down, left, right, select, and then I could move a pointer in a computer. Another thing that we have that I must introduce for EEG, for BCI, sorry, is that we have two types. We have synchronous and asynchronous. Synchronous would be that the system is going to tell you within this window, you must think the action you want to do. It is easier to implement, but problem is that the person needs to wait to that window. The other way is the asynchronous, that is what we would like. This is the way we act normally. So the system should be able to detect when I start thinking or when I start imagining a word. And then detects, okay, this guy starting imagining a word and then it finishes. I took this window and then I'm going to classify. And then I'm going to perform the action. So, in a brief summary, we have visual evoked quotation BCI, movement imagery, and we focus on imaging speech BCIs that use EEG. So now that we kind of understand a little bit of background, let's go to the problem statement. In order to detect these words in the continuous signals, we want to do it for the implementation of the asynchronous BCI. We have to first detect those segments, those parts where the word is being imagined. These windows are not fixed because some words are longer than others. So you cannot just like have a normal window and apply it. You have to detect many windows and then detect when the word starts and when does it end. This is the first problem, and this is our first research question. That is it even possible? Can we do that? Is it even possible to detect when the subject starts to imagine a word and when does it finish? That was the first research question that drive this presentation. So basically, we have the signal, and let's say at some point in some window, we have the imagined word. We should get a model, so we need to apply all the machine learning process to transform this into instances, put it into a model, and then the model is going to classify us small windows that are going to be moving and are overlapped, and are going to classify us as one of two: imagine word segment or idle state. Idle state is defined as whatever you think. Just think another. Your mind is just flying around doing whatever you want. But if you start to imagine a word predefined from the dictionary, it should fall into one of these. This is like the first problem that we have to solve. The second problem is, okay, now we were able to detect the start and the fin and the end of the imagined word. Now how do we know what word is it? We have to define a dictionary, and then from those dictionary, we have to apply another classification, another machine learning model with another features to detect the word. Then in this case would be left, and from that classification, then send the the signal or the order or the action to the actual BCI. Just as a recap, or if we are not really familiar with machine learning it's the process or the way of make a machine to make a computer to do something that was not explicitly programmed. So we have to train a statistical model, any other type of model we want, to learn the statistical properties of a data set. For if the model detects the whole statistical properties of a data set, and then we input a test instance, the machine learning model or the AI model should be able to detect to which class does it belongs. There are many types of machine learning models. We have supervised learning, unsupervised learning, we have reinforcement learning, generative AI, we have classification, we have regression. We just care classification. I send something to my AI, and then my AI is gonna tell me it's A or B. In our case, we want to detect if it is an idle state or an imagined word segment. And then the data set. Because to train any machine learning model, you need data, always. So we collected 3 data sets. The first 2 were to 27 subjects using this thing that is called Epoch. It's a 14-channel system, 128 hertz frequency rate. And this is the placement. We use it because it's very cheap. It's kind of $1,000. And we could collect to our students this database. The third one was with another one that was shared with us or donated, I remember, by the WAP. And it's a bigger one. It has 64 channels. This is for clinical purposes. And it has 500 hertz. They did it with 20 subjects. They were doing collaboration research. So we use these 3 data sets. Of course, in order to normalize or to get the same standardization from the third data set, we had to do a downsampling from 500 to 128 and select only the 14 channels that we're using on the first one. How were those data sets? Well, those data sets basically you sit the student or the subject in front of a screen, and then they can perform several activities. In the first one, they were allowed to imagine the world whenever they want. So they were like, I'm doing nothing. And it was like, imagine the world up 5 times. Okay, up. To have the ground truth, they made a click. This is a big artifact that had to be removed because if you have that click, of course, you're gonna have a big spike in your EEG signals. Oh, but you're cheating. That's why you cannot do that. So we have to remove that. The second one was more controlled to avoid this problem. So you have first a cross, and then a word was presented, and then you have to imagine. So the windows were already predefined, so we could act before better with them. And then to avoid,
Lo veíamos venir.
really, she's gonna come back like in 1 minute or so. So it's normal.
Pues, pero sí,
It's normal.
Okay, let me check because maybe somebody turned down the switch.
Okay. Yeah, cool.
you know which switch?
In Doctorado's office, there are switches like this. So,
Sí, pero energía hay. Aquí llega por los cables.
Cierto, aquí sí llega.
Pero la pantalla no detecta nada.
Ni siquiera está prendido acá tampoco. Sí, pero es el wifi, ¿dónde está?
Maybe we should move our seminar to other place. This is happening
El wifi viene
almost every
por el cable de Ethernet, es algo muy extraño.
¿Está corriente?
Tiene 2 cables de Ethernet, uno es de señal y otro es de
They
corriente.
are doing this construction.
Eso no sabía. No sabía que el internet puede mandar señal que diga corriente.
Es en principio, ¿no? Solo
Pues un cable.
es un cable. pero es muy delgado
They are
como
not
para que
switch off
igual
the-
También,
mande los 120.
también pues, es un modem, ¿no?
apostaría que es la casa que ves cuando vas a hacerte el examen.
Probablemente. Pero como la tomamos de la guapa, es una
Okay, so now we will coffee.
Es más barato que me quisieron vender.
Ready? Okay, so we were talking about the 3 data sets that were taken. The whole point is that the 3 data sets, no matter how was the protocol, they contain the same way. We have a single state segment, different for each one of the data sets. So we could do a broader research. The part where the word was imagined that we want to detect, and then another single state segment. We have different trials. Trial is a segment like this. Lots of trials per subject, and 27, 27, and 3. So we have lots of data to work. First, before putting anything to a machine learning model, you have to extract features because you cannot put just the raw signal, because the raw signal is 14 channels with 128 hertz. So you have lots of data points. You have a matrix that is unmatched. You cannot deal with that. So you have to extract information from that. You could go from the simple thing that could be the mean, could be the variance, or any other statistical, but those statistical parameters work for very simple things. For complex things like this, we have to apply other several things. The first thing we have to do is we have to clean the noise, all the noise. So you have to first remove 16 hertz signal because you have cables there. Unless you have a completely isolated room, it's gonna be a lot of noise. And then you're gonna use a system that's called common average reference that basically you take an electrode and then make a comparison with all of them. And you extract anything that is same to all of them. So you can, it's a way to remove noise. It's a first approach to remove noise. And another thing, as we said, we have to detect by mini windows. So we have to do 2 types of segmenting of the windows. If we are going to use the training data set, or let's say the data set from which the model is going to learn the statistical behavior, we can make use of the markers because it's going to be the training. So we can make use of the markers to segment several windows and then train the model in a binary classification. But if we are going to use the test set is the one that is going to simulate the real world. So in the real world, you don't have these things. Otherwise, it would be necessary to do all these things. So we have to take the signal, a window that is going to be moved all over the place. Of course, we're going to have some problems here. Maybe here is going to be detected, okay. And once we enter here, we're going to have a problem. Because it's like, how do we take it? It's an imaging for segment or it's an industry? And then the next level is to decompose the signal. As you may know, an EEG signal, it's noisy by nature. It's a stochastic signal, contains lots of information, but it's very, very noisy because you can think something and in your mind, some electrical activity is going to spike. But in the way that comes from your brain to the scalp, have lots of noise there. So there's a very bad signal to noise ratios, so you have to apply decompositions. The 2 decompositions that we used was first the discrete wavelength transform, the second one the empirical mode decomposition. The wavelength basically is like a super Fourier transform. We know that we have our signal, we are in the space of amplitude time, and then we apply Fourier. And if we apply Fourier, we're going to go to frequency and amplitude. frequency and amplitude. But there is a problem with Fourier. Fourier assumes that the signal is stationary or that the frequencies are stationary. So what happens if we have, let's say, if we would like to analyze a whole symphony with Fourier, we're going to have lots of noise because we're going to have lots of frequencies over the time. And Fourier by itself does not take into account that. Wavelet transform is a transformation from amplitude time to a three-dimensional space that is frequency, amplitude, and time. You can do it continuously. It's computationally very complex, but you can apply something that is called distributed transform, so that you make it in small windows. So you apply from small windows of time. So it could be like applying Fourier many times, and then getting this decomposition. The second decomposition was the empirical multi-decomposition that basically decomposes the signal into what we call modes or intrinsic mode functions. These modes detect the oscillations or the frequencies of the signal. So it decomposes in different oscillations. And in this way, we can remove the first one that is the most oscillatory, that will be the most random noise. And then we could take, for example, if you have an envelopment, we could take the sine signal or whatever other signal that we make use of it. And then the funny part, the features. Once we decompose the signal, the only thing we are doing is getting more signals. Still, we cannot deal with it. It's a very high dimensional. You have to extract features. As I said, you could use mean or variance, but those are very simple. So we use let's say five important or five characteristics that we thought were related to the nature of the signal. The first one is the instantaneous energy and Tiger energy. Those are extracted from the wavelets and from the intrinsic mode function because the energy knows the square value, and it detects us how big is the power or how intense do we have there. And of course, it's not the simple energy. We have this system that detects a little bit more information. And the last three are related to fractal dimensions and chaos dimension. Why? Because here is where it comes the second research question. Remember, our first research question was, is it even possible to detect it? Second research question is, okay, let's say we can do it. How can we do it? What is the best way? And something that we may think by nature is that EEG signals contain chaos by nature. So we could say, okay, let's use some chaos measurement. There are lots of fractal measurements functions. Let's take it and see what happens. And we use the Higuchi, CATS, and generalized Hertz-1.
So what is your M?
Yeah, basically, I didn't put completely there because it's very, M, it's, you have a signal and then you're gonna do like a difference from the first and the last one, and then you're gonna start getting some distances. The Minkowski distance between a point and different points. So basically, you have a signal, then you transform it by applying some distances, and you're gonna have another signal, and then you get this logarithm.
So that's your D.
No, D is the distance only between the 2 points. The
Okay.
And M is between. I don't quite recall it, but I believe it's between the mean. You have the mean and the distance of all the points to the mean.
Because from the expression, it's analogous to mass. That's why I'm trying to understand what is analogous to mass here.
It may be.
Okay. And what is your K? I'm sorry.
K. I should have brought the paper. I don't recall it by heart, but basically you apply also a transform to the signal, and then you get this function, the L over K, that is, I believe is the number of differences or something like that. I'm not really sure. I don't remember. I have paper over there. Okay. I can check it again if you want.
Should be a multi-factor.
Yeah, it's like a
It's a
multi-fractal.
fractal.
That's why I'm asking.
Yes. Yes.
It's a multi-fractal.
Yes. It's to measure the fractality. Yes.
Yeah, but it's not a simple fractal.
Exactly.
It's a multi-fractal.
Mhm.
So that's why we can see from it's very clear from your second formula that M is your, for the standard multifractal thing, M is something analogous to mass. That's exactly what I'm trying to
Yeah.
say. Not the Higuchi one, but the first
Yeah.
one.
The
is-
cats. Yes. Mhm. Yeah. Okay. From those functions, we build 5 feature sets to train lots of models. The first one were only wavelengths, the coefficients of the wavelength. So basically, it could be like frequencies and time, just like that. From the second one, we decompose the signal into modes, and from that decomposition, we extract all the functions that I mentioned to measure chaos and fractals. Then we use only the Hertz exponent directly to the noise without just clean, let's say, the common navigator reference to remove the first level of noise, and then the rest just like leave it as it is, and let's see if we can check something. The 4 and 5, 4 basically are the 3 of them just as a big one, in order to say instead of getting separated, let's say that maybe you can get information from one or other. Let's take the other one, and the 5 one is the same as the 4 one, but with a PCA or principal component analysis. The composition that basically what it does is you have your signal, you have your signal, and then you're gonna have the eigenvectors of the correlation matrices between the channels, and then from all of that you're gonna take those dimensions or those vectors that contain the majority of the information. So if you have lots of points, and we would have like an ellipse and like lots of points, noise, we could say, okay, let's just forget this axis and then collapse everything into this axis, let's make a projection, and we are losing information. Of course, we are losing information from the second axis, but to do so, we gain the thing that is the cross of dimensionality. So we reduce the dimension, and we can train models faster, because training models in a big data set can take hours. So this was just to prove that we can maintain the accuracy with less features, and this one was to prove if measuring the fractality could help. Just in a summary, we have the signal. To remind you, we have the signal from all the channels. Then we apply the signals composition. Then we have groups, sets of signals, mini signals. From those signals, we extract the features, and then we're going to get a feature vector. That is going to be just this number. And this feature vector is now the one that we are going to use. This is our real training set and test set that we're going to use to train the machine learning model. Quick reminder of
just a confusion.
yeah.
So when you define this feature vector,
Uh-huh.
it's similar to agent-based modeling, or there is no connection with that?
Similar to what?
Agent-based modeling, or it's no connection with that?
No, agent-based it's another stuff. Just to remind, basically the pipeline of any machine learning is we get the data, we already got it. We clean, prepare, and manipulate. That we already did. We got the feature vectors. Then we train the model. Then there are tons of models, classical models or deep learning models, whatever you want, to let the model learn the characteristics of the data set. Of course, you have to split it into a train and test. You cannot test with the same training without cheating. And then you apply the testing, and if something can be done, then you improve the cycle. We use 4 classical machine learning models. Back in that time, there were no supercomputers, but actually we did some deep learning stuff after that. But for this thing, we say, okay, let's just go with simple machine learning models. The first one was a random forest. Random forest is basically a decision tree, but instead of having just a decision tree, you take lots of decision trees, a variety of decision trees, and then you take the majority vote. KNN is one of the most simple. KNN basically you have a cluster of data, and then you define the class by getting a measurement between each of the vectors and the closest neighbors, and use each one to be similar. Logistic regression. It's like a neural network, but we're just one neuron. Sometimes it's very simple, but it's powerful. And most important, the supervised machine is the one that I like the most. Basically, what it takes is you have your feature space. There are a bunch of vectors, and sometimes they are mixed very nicely. And you want to make a separation line or a separation plane or whatever you want, or surface. But sometimes you cannot do it because they are like intertwined. The objective of the supervised machine is to find a kernel that is a transform that is going to transform those vectors into another feature space where they are separable. So it could say the most simple one is if we have a square function, we have a problem, we have a square function, and then let's say that those values and those values belong to one class, and this part belongs to another class. In principle, you could not do something, but if you get it to another dimension, you're going to have a plane. And well, we did 75 training, 75 testing, applied a four-fold validation because we cannot just do it once. Otherwise, we're going to say, okay, maybe you just got lucky. You have to apply it several times. And this is something important. We train models by subject. We do not train models to all of them. We tried. It didn't work. The explanation of that is that a difference with the movement imagery. When moving imagery, we can move and everything is in one part of the brain. Imagine speech, although is in the Wernicke and Broca's areas, the way I imagine the word up is not the same as you do it for any other. I may do it. I may do it over and over again, and it's gonna be the same patterns, but it's not the same as other people. So this is completely different. Imagining speech is something completely different. And to your question previously, Soham, that if it's the same that if I speak to you, in principle, no, because the hearing processes in the temporal lobes, and imagining speech, although it is mainly in Broca and Wernicke's areas, we found that there is information all over the head. So it's a process to talk. It's a very complex process. And after that, we have to remind that after making the classification, we did it first by windows. So we're going to have things like this mini windows of idle state, then imagine work, idle state, imagine work. So what do we do with this? Doesn't make sense. And also doesn't make sense because we have overlapping windows. So we have to deal with it. And the way we did that is to take the size of all the overlapping, all the windows that share the same information, and we do a majority proof. So with this, we transform the 0.5 second window into a 0.1 second window, mini window. And then after that, we could get this type of things, or maybe a blank space here. So we applied first neighbor error correction. So we like the spin, it would be like spin if you got spin. Do that, you do exchange. And after that, it will result. Oh, okay, doesn't look okay. Okay, yeah, use that. We have things with the resolution. Yes. No. That's okay. It's good for the resolution of this. You want to just make a zoom or? Yeah, it's better. Yeah, just get it like this, and then we zoom out. Just explain. Okay. We have five plots of box plots like this one. Each one is for each one of the data sets. For each one of the data sets, we have 4 sets. Each set is for each one of the classifiers. Remember, we use 4 classifiers. And within the classifier, we have 3 feature sets. In this case, first, remember we have 3 data sets, so that's why we have 3 plots. We have 5 feature sets. First are presented only the first 3 the first 3, and then the last 2 to make a better comparison. And each one of the box plots are the results for all the subjects. In this case, for the dataset 1 are 27 subjects. The black, the white one is the mean. And the first things that I can see, okay, it's very, very spread across the subjects. It's a lot of noise across the subjects. For some subjects it works okay. From others, it doesn't. We tried to find that was another research. Why? Maybe some people did not get concentrated while taking the data. Maybe there was too much noise. Maybe they were stressed out. I don't know. There are many things. But
F1 score.
Sorry. F1 score. Yeah, sorry. F1 score is the harmonic mean between the recall and precision. When you evaluate a machine learning model, the most typical measurement, evaluation metric is the accuracy. Basically, just take all the good classifications and you divide over all the amount of classification. That will be just the percentage. But we have a problem with this. If we have an unbalanced data set, this is going to take us to bad readings, because if I have 99 instances of one class and one instance of another class, and then I classify everything as the biggest class, we're going to have an accuracy of 99, and that's wrong. In order to solve those problems, we take other 2 metrics that are precision and recall, that take the differences from the relevant classes, how many did we take, and then we apply the harmonic mean. Harmonic mean is when you have fractions, and the harmonic mean is the F1 score. It's a value that goes between 0 and 1. 1 is the best, 0 is that is wrong, and 5.5 is basically the random model. It would be a model that classifies everything as random, that does not learn anything.
But this is about recognizing the window.
The window that if you are speaking, if you are imagining work or doing other stuff. That's why the random choice is 0.5. If we would have a 5 class classification, it would be 0.2. Those are very, very good results. It may look like, okay, they're very bad at 7, but for a complex task like this, those are very, very good results. Obviously, the p-value between the random one, that is 0.5, and those values is way smaller than 0.05. So, okay. With this, we can prove the first research question, that is it possible to detect them? Yes, it is. There is a and okay, there are the other 2 plots. I have a table after that. I have a table after that. We can avoid going through all of them, but basically we have those 2 plots, and then this one. This is for the last 2 feature sets. We can see that the blue one is the one that applied the BCI, the BCA that took all the features and then applied the BCA, and still behaved good. So it was like, okay, it can help us. Here are the more detailed results. For the first 3 feature sets for each of the data sets, it was the value for all the subjects. We could see that we could check like, okay, concatenating everything gave better results. Yeah, but it's not too big. And the variance, the standard deviation is too high. So after applying a statistical test here, the p-value is too high, ridiculously high, like 0.6 or 0.4. So with this, and comparing the different feature sets, we could check that in most of them, it was either the second one, or the first one, or the last one with the PCA. So the second research question, that is, the measuring chaos fractality from the signal helps us to get a better classification? No, it doesn't. At least not with these measurements. So that's why we didn't go so deep there. But it was an interesting thing, and it was important. The most important thing that we find was that we could reduce the dimension and still get good results. Good results, and that it is possible. So this is good because there was no baseline. There was no research back in that time that dealt with imagine speech segment and input state segments. There were research about word classification, but they did it already getting the predefined window. Detecting that window, there were no research, so we had to start with something and look at the results. Fortunately, they always did. So, well, as I said, the feasibility to classify, yes, it's possible. P-value way too lower than 0.05. Proven by chaos? No, it's not. Then we went into the data sets to find why one dentist went better than the other, and we realized that it was because of the product. Sometimes the ones that behave worse were the ones that took very, very longer, and it's very exhaustive for the subject to do a session like this. The one that was randomized was the one that got better results, maybe because the person was not like engaging in a word and we're not thinking the same. It's like when we are doing something repetitive and then we enter in an automatic state, and then we start thinking about stuff and we are doing the same like when we are trying.
So you have all the correlation.
Yeah. And yeah, well, the PCA helps us to apply smaller models with the same metrics. Well, this is conclusion for the first part, everything I just said. There is a second part. I put it just no, there is nothing. Okay. There's a second part where we made the classification of the actual words. Of the actual words from the window, we made the classification of the dictionary by introducing a deep learning model based on fuzzy sets, based on fuzzy logic. It was good also, but maybe that's for another day. To verify.
Yes, I have a question. So all the work is about Mayan words. But is there a way to really see the difference between an Mayan word and an Mayan action? For example, at the beginning you say that
Imagine movement.
Imagine movement. If somebody thinks on moving the pointer on the computer, I can think on the word move, but also I can imagine the pointer moving.
Yes.
So is there a?
If you mean like imagine movement, yes.
But can you really tell the difference between those signals?
You cannot tell because that is why that was a question of why we could not train a general model for all subjects. Because maybe I may think up, but it's not like, or maybe for some person the words appear in your mind like up.
Yes,
or maybe it's an arrow.
Yeah,
I don't know. Maybe you think of the concept. But the important thing is that no matter how you do it, if you do it again, you're gonna do it the same.
yes.
So then,
So what if I cheat?
cheat.
Like I'm thinking sometimes arrow, sometimes a letter.
Mhm.
People
Yeah,
do
and
that.
yes, and that could lead us to bad results. That's why we did it with many subjects to avoid that.
Okay.
There could be people that did that were cheating, or that maybe they were already tired. I mean, it's half an hour. Maybe they were like after 20 minutes they were like, whatever. I just want to get out of here, and they just think random stuff. And that maybe where we get
And it may not be cheating, right? It could be very natural. My point is that for teaching, for example, same thing we teach in different ways, right? So personally, when I write an equation, my notations from one semester to another semester completely change.
yes.
So that's natural trail for something,
Yes.
right? So then you really, then that cases it will not be same, right?
Yes. Yeah, because when we did a deeper research, but that this was not like something objective, but it was among the students. So we knew all the students. It was master students. There were master students from all over the institute. The institute is very small, so we knew each other. And when we did the comparison, then we went subject by subject, like why this subject always performs good with all the models. Why this subject is very clear. And then we went and analyzed that those subjects were the ones, not the ones that were more trained, like us.
Yeah.
The ones for the core group. Like, of course, because of the core group, because we have done this tons of times, and we know how to do it.
Okay.
And then for other people, maybe they choose the first 10 words to understand what was happening. And this is also part of a normal training of any BCI. Any BCI is personalized, and after they use it at the beginning, it's just pure noise, and then with time they like learning to drive.
What were your results for the differentiation of words?
Words.
Maybe you can just show us.
Yeah.
If you last.
I can go quick. I can go quickly. Basically, we define a deep neural network where each neuron, instead of being a logistic regression or a ReLU, it was something that we call AMPHIS. AMPHIS is an adaptive neural-fuzzy inference system that uses fuzzy logic. The difference between fuzzy logic and increased logic, you have something that either belongs or does not belong to the set. Fuzzy logic, instead of having that, you have a function that is a belonging function, membership function that goes between 0 and 1, and it helps us. It is very good for nonlinear and chaotic and nonlinear data, but it's very slow. To avoid this slow thing, we transform it into a tensorial form, and then we applied GPUs to train this, and the system was the same. And basically, these were our results. Quickly, we would just move the light per second very, very small, and it never work. It got 0.2, that is the random one. It means it didn't learn because there are 5 classes. There are five words: up, down, left, right, and select, because the words are about one. In this area, there were already published results. So the research question here was not if it was feasible to detect the words. It was already done. So it is already feasible. The research question here was, can we do it with smaller models? Because they did it with deep learning. Deep learning, and they use ridiculously complex models. And what we got is that we could achieve similar results with a very, very simple network. Just 2 layers, 10 and 5 neurons. This is a very, very simple network that we did the same with the multi-layer perceptron. And that is a simple neural network, just to prove that it is learning, and the other one is not feasible, and the time it's not that bad.
This is again for individuals, right?
Yes, for individuals.
So
Yeah, there
we
will
cannot generalize.
no, we cannot do that yet. And yeah, basically that was so it could also be done.
Nobody has questions. I have another question.
Yeah.
But it's a little off topic. I'm just curious about how do these detector works? I mean, it detects electric signals.
Yes.
But you say that one of the methods to reduce the noise is to check the detection of all the detectors, right? So that means that in my brain or in my head, the same signal is in all my head. It's not in the specific.
Yes, it's in the maybe it's higher in some points, but the weight from the neuron, that the neuron is not in the surface of the brain. It's inside from the neuron through the skull, it dissipates.
For example, blood flow.
Yeah.
Blood flow in the skull that gives you a specific signal. So you have to remove all this.
Okay. And okay.
This electrodes, you mentioned electromagnetic.
Yeah. Yeah, electric.
Electrical form currents, which are flowing in the brain.
Yeah. There,
But they look at it from the distance.
And how many electrodes do you have?
14.
Oh, okay.
14. Yeah.
No, but they are anyway overlapping, so it makes no sense to divide it.
No, that's all.
Yeah, but 14 is pretty decent. My point is that EEG people do it with 50, right? And they're extremely reluctant.
But yeah, 19, that's one with 64 channels.
Yes, exactly.
Yeah, 64 channel, that will be,
We did it.
But it doesn't really help.
yeah, that's exactly my
Uh-huh.
point.
Yeah, we did it, and also we kind of trained it. It was a pain because the
Yeah, because
dimension-
there's a lot of redundancy, right?
Yeah,
64 channel.
exactly, yes. But the good thing, the 64 channel is that as it is clinical, it's kind of more precision, more precise than the other one that is commercial. But also we went into the commercial because we thought that for later applications, you're not gonna have a clinical skull. You need something, this thing you can make the setup in 3 minutes. It's easy. From the clinical, you take like 15 minutes.
Let's now that you did this stage,
Yes, exactly, yeah.
you didn't try to look at correlation. So correlated feed, so the does it play a role, or is it somehow detectable if there are features, if there are correlated features, or is it independent?
I don't remember, I did the correlation matrix of all the features, but I don't remember the results.
But did you see any correlations?
Yeah, but not kind of too high. I mean, there was.